questions, or you can raise your hand. I should be able to see that. I got both my screens right here. So again, I want to see what I can learn about chemistry here. So let's do a classic example using the particle in a box to predict something about chemistry. And you're going to see this idea in the third rotation in your labs this semester when you do the dyes lab. It's the second formal report lab, which uses the particle in the box model to model how basically optical dyes work, absorbing dyes work. Right? And I kind of want to play with that idea today. Very simple idea. So I want to look at a very particular molecule today, 1,3-butadiene. A very simple molecule. And if I were to draw 1,3-butadiene, it's just basically two ethylene molecules stacked together like this. There's two isomers. There's the cis isomer, which looks like this, and there's also the trans isomer that looks like this. The trans. And it turns out that the trans is more stable. So this is actually the preferred form. All right, and what I want to look at is a particular part of this molecule. So what I want to focus in on, let me draw this trans again. I want to think about the double bond system of this molecule. Sorry, let me draw that. All right, so if we look at this molecule here, again, we have carbons at each of these vertexes. There's carbon here, carbon here, carbon here, carbon here. And just from organic chemistry, we know these carbons are sp2 hybridized. All right, so they have an s orbital and two sets of p orbitals contributing to their bonding, which leaves one additional unhybridized p orbital. Right, there's three of them. We've only used two of them. For each carbon. And these exist perpendicular to the bond. So if you think about this butadiene being planar, right, it's a straight line effectively, that's curved, but you can think of it as a box, a flat box. There's these p orbitals that sit above and below the plane, these unhybridized p orbitals. Like this. All right, here's our unhybridized 2p orbitals. All right, and if you do the electron analysis, you count the number of electrons and carbons and all the bonds and stuff. You've probably done this in organic chemistry. You have one p electron left per carbon atom. So each one of these carbons initially has one electron in them. Right, I'll just kind of put them in here. All right, so there are 4 p electrons shared amongst the 4 perpendicular, this is perpendicular, this sign right here, perpendicular, p orbitals. Okay. All right, we'll talk more about these, and we'll actually work out the math in detail later in the class when we talk about molecules. But again, I'm not using anything more interesting than regular old sp hybridization. Right, and we have a name for these orbitals, right? So when you think about how do these orbitals interact with each other across the bonds, well, they have bonding interactions. They have some overlap between them like this. All right, these orbitals can share electrons across them, right? That's the point of a bond, to share electrons. Right, and you form these combinations. These are combination of p orbitals. Atomic p orbitals in this manner are called pi orbitals. You might have heard that term when you did organic chemistry. Right? There's these pi bonds. Right? And the pi bonds are just these cylindrically symmetric, like, combinations of bonding orbitals. Right? These just is a pi orbital of the molecule. Right? These are what we call molecular orbitals. We have atomic orbitals, which are orbitals, right? They're wave functions corresponding to electrons on a single atom. And then we have these pi orbitals, which are collections of the p orbitals, and they're all interacting together, right? Sharing electrons through the bond. Right? These are pi orbitals. Right? Don't need to know anything more about this except that there's this chain of orbitals that has 4 electrons in them, and they're being shared roughly equally amongst all of the carbon atoms. Right? We can always draw a resonance structure for this trans configuration, where you localize the double bond here, and you kick that hydrogen there, or that electron there, and you get, again, the same structure. You have a double bond in the middle, and you have a plus charge on the end and a minus charge on the edge, on the other edge. Right? So we can charge separate this, right? And this just identifies that these electrons, they're distributed, they're delocalized, right? We call that delocalization, which means that the electrons aren't localized on an atom, but they're localized across the entire molecule, right? They can move from one atom to another. They're shared. All right, I'm sure you guys know these as conjugated double bonds, right? You see this in benzene and anything that has alternating double bonds, you see this behavior. Okay, and this is the general structure of them. So what I want to do is I want to model this pi system, just these pi electrons, with a particle in the box. The idea is this. If I were to look at the energy levels of the molecule,
slide real quickly.
Oh, yeah, I'm sorry. Go ahead. I'm sorry. Go ahead. So the idea here, you just need the right side or the left side?
The left side. I'm still getting the stuff with the P or.
Oh, okay. All right. So I'll keep talking while we write it here. And in fact, I'll just continue drawing this on the page here, so we can keep everyone catching up. I'll talk slowly. So let's think about the energy levels of the electrons. Of electrons in this molecule. Okay? So there's a bunch of energy levels, I don't know how many. Okay, and we're going to fill these orbitals up, these energy levels up of electrons. All right, and we're going to go through all the sp2 ones, all the ones in the single bonds, and stuff. All right, so we might add some electrons. Remember, you can only have 2 electrons per level, right? Just like in the atoms, right? You can only have, the Pauli exclusion principle says you can only have you can only have 1 type of electron per energy level. And there's 2 types of electrons, right? White and black, or spin up and spin down. So you can have 2 electrons per level, right? We can fill these up with our sp2 electrons, right? These are our sp2s. There's many of them. Okay, but they're all in strong bonds, right? The single bond and the main part of the double bond and carbon-carbon bonds are very, very strong. These electrons are very low in energy. They're very deep, right? They're very stable, all right? But eventually we're going to get to higher and higher energy, and as we'll see, energy correlates to distance from the nucleus. These p electrons that are kind of in the pi orbitals, they're far away. They're higher energy because they're less shielded from the nuclei, and so we eventually start filling up the higher orbitals with our pi electrons, right? And there's 4 of them, right? So here's our pi electrons right here. Okay, now I'm going to make an assumption here. I'm assuming, and this is a reasonable assumption for the most part, we'll see how reasonable it is, that the sp2 electrons are independent from the pi electrons. They don't interact at all. Right? So what I can do is I can write a wall here, right? That the electrons above this wall don't interact with the electrons below it. All right? It's as if the sp2 electrons, they're their own little block by themselves, right? And they're non-interacting. Okay? They're what we call core electrons, and they're non-interacting. Okay, so we can basically ignore them. They're like a background. Okay, so what we're going to do is we're just going to ignore all those deep electrons, and we're only going to look at the pi system. All right, so we're going to treat this pi system here, this set of states where the pi electrons are, as a particle in a box. Okay. So let's just consider the pi electrons at the highest energy, these what we call the valence electrons of the molecule, or the frontier electrons, the ones on the edge of energy. We're going to treat them separately from all the other ones and treat them like a particle in the box. Now I'm hoping Dan's all caught up so I can keep moving. Okay, very good. So we're going to make an assumption here. So first of all, remember our box is one-dimensional, but this is a two-dimensional molecule, right? The electrons kind of travel back and forth through 2 dimensions. All right, so what I'm going to first do is I'm going to make this a line, make molecule a line. All right, I'm going to stretch the molecule out so that it kind of looks like this. We have H's here and H's here. All right, so same molecule. I've just made it a line. Okay, so I've stretched the molecule out. Right, that'll now makes it one-dimensional. Right, now we can treat it as a line. Okay, and what's the length of this line? Well, it's the length of approximately 3 carbon-carbon double bonds. Right? And that's about 1.3 angstroms. Okay, so the total length of the molecule is 3 times 1.3 angstroms, or the pi system, rather. So the length of our box is this, and we'll just say it's roughly 4 angstroms. Okay, I think that makes things easier. Okay. Now what we're going to assume is that the electrons, right, there are 4 of them, the electrons act independently, right? They don't interact. Okay, so what that means is that the physics, so the energy of one electron is approximately equal to 1/4 the energy of 4 electrons. Right, they're just 4 identical electrons moving around. Right? We're just kind of assuming that they don't talk to each other. Right? That might seem like a bad assumption, because if the electrons are close together, they're going to repel each other, right? So that means that if there's an electron nearby, the other one will see it and it will affect its energy. So we're going to ignore that, all right? We're going to see how good this result gives us, but we'll ignore it for now. All right, so those are our 2 assumptions. And then what we're going to assume is, again, particle in a box, which is the line thing. And we're going to assume electrons, if it starts writing, electrons, fill the box like an atom, which means 2 electrons per energy level only. Max. Okay. Now this is not an assumption. This is just fact of life. Okay, so this isn't really a simplification. This is just the way it works. So electrons have this property. You can only put 2 per energy level. 1 spin up and 1 spin down. Right? We call that Pauli exclusion. So now let's write our little energy. Again, we have our little particle in a box energy levels. With n equals 1, n equals 2, and n equals 3, for instance. And we fill these 2 at a time. So there's going to be 2 electrons at n equals 1 and 2 electrons at n equals 2. Right? So this is our ground state. Right? This is the molecule's electronic structure when nothing's happening to it. Right? We just have a normal molecule sitting around, not doing anything. And what I want to predict is, where do we expect to find... Now let's imagine we put this molecule on our spectrometer, right? We're going to measure the absorption. We want to measure where the molecule absorbs. So what does it mean for a molecule to absorb? Well, let's just use the very, very simple definition that we use in general chemistry. An atom absorbs a light when the light is the same energy as the energy level difference between the ground state and the first excited state. So what we're going to do is we're going to shine some light into here at some frequency. H nu, this is my light. And we're going to take this one of these electrons and promote it here. Right? So ultimately what we're going to do with this light is excite an electron from n equals 2 to n equals 3. Right? So that means that our molecule will absorb at a frequency equal to the energy difference, which is E3 minus E2 for the particle in the box, the energy difference between the third and the second level. Okay. All right, so we can calculate that. We know the formula for the energy for a particle in a box. We've written it down. We derived it exactly, right? So I'll just write it over here on the side. Remember, En is equal to n squared h squared over 8 times the mass of the electron in this case times the length of the box squared. Okay, so all we have to do now is calculate that. So that's going to be, I'm going to factor out all the constants. That's h squared over 8ml squared. And then we have n squared left, so that's going to be 3 squared minus 2 squared. Right? And that's easy, right? That's just 5. So the energy difference between these two levels, right, the first excitation of our molecule is at 5h squared ml squared. 8ml squared, excuse me. Okay, so all we have to do now to calculate this energy is just plug in our value for h, our value for the mass of the electron, and the length of the box, which is 4 angstroms. Just as a reminder, if you don't remember what an angstrom is, it's 10 to the minus 10 meters. Okay, and again, this is the mass of the electron, right? Because we're thinking about an electron moving between different energy levels. And so when you calculate this number, I'm not going to work it out exactly, it's just a plug and chug. It's 9.02 times 10 to the minus 19 joules. Now that number is not particularly helpful for us because remember, we're shining light at it, right? So we have light of a given wavelength or frequency. So what we need to do is convert this energy into a unit that's more appropriate for us, which would be wavelength, right? We were going to have a laser or some sort of light source shining through our material. We want to know the absorption is a function of the wavelength of our light. So how do we get from joules to wavelength? Well, all we need to use is Planck's law. Right? It says that delta E, the energy difference, or the energy of that photon, is h nu. And the frequency of the light times the wavelength of the light is equal to the propagation speed, which is the speed of light. So this means that delta E, the energy difference in joules, is equal to h times the speed of light over the wavelength. All right, so all I have to do is just take this 9.02 times 10 to the minus 19 and calculate it. So let's go ahead and do that. All right, and I do that, and you get 220 nanometers. All right, you get 2.2 times 10 to the minus 10. Sorry, this is wavelength, sorry. Let me just be precise. So the wavelength at which this electron absorbs energy is 220 nanometers, based on this assumption. Okay, so that's in the blue. In fact, that's ultraviolet. You can't really see 220. It's right on the edge. But it's somewhere on the order of the ultraviolet, the weak ultraviolet. And I don't have a lot of room here, but I'm just going to write it kind of in the corner here. What the experimental value for this is, it's 217 nanometers. Or sorry, this is the experimental value, not max, sorry. All right, so we've predicted it at 220, and we're within 3 nanometers of the actual answer. All right, so that's about 1%. We're off by 1%. All right, that's pretty impressive. I mean, we just have to stop and think about how good this prediction is, right? We've made a lot of really, really big assumptions here. First of all, we've gotten rid of the fact that the molecule is not one-dimensional. It's two-dimensional, right? It's a little, right? It moves to the up and then to the right and up, right? It has some two-dimensionality to it. We've also assumed that every p orbital is exactly the same and that the electrons are free to move around them. And it turns out that's also not true. We'll see that later. That these p orbitals, the ones in the middle of the molecule, are different than the ones on the edges. Right? But we've assumed everything is exactly the same in this molecule. All the lengths, carbon-carbon lengths are the same. All the carbons are exactly the same. They all share electrons equally. We've made a lot of assumptions about this molecule, which turn out to not technically be true when you look at it carefully. But we're going to assume it anyway, just because it makes our life easier. We've also assumed one of the worst things that you think you could possibly do, which is that electrons don't see each other, right? That they act independently, right? That's the number 2 assumption we made. And in fact, that's a really big one. Right? You would be worried about that because you know electrons repel each other. So if you have 2 electrons in the same kind of region, they're going to push each other apart and it's going to change their energy. But the fact of the matter is that even though we've made these crazy assumptions, we get to within 99% of the correct answer. Okay, and that's not a coincidence, it turns out. It turns out that this assumption is an assumption, this kind of idea that we use, the idea that electrons on average don't really see the other electrons, or if they do, they see an average cloud of electrons, right? They see some average quantity of the electrons around them, but that could be 0 if they're sufficiently far apart. Right? We make this assumption all the time in chemistry. In fact, that's one of the most important assumptions in all of chemistry when we compute stuff, is that we might not know how the electrons interact with each other, but let's just keep it simple and make sure that they all kind of interact independently of each other. Okay? That they're all kind of individual bodies. It's a very reasonable assumption to make, but it's a wrong assumption because it's not true. Electrons do interact with each other. Right? If you go look at a magnet, for instance, if electrons didn't interact with each other, there would be no magnetism. Electrons are important, and they do interact with each other. But the point of the matter is that it's, even though it's incorrect, the interaction between 2 electrons in this molecule is actually very, very small. It's diminishingly small, to the point where by making that assumption, we're off by 1% of the actual value. So what does that mean? Well, it means that the dependency of electrons on themselves, the communication of electrons between each other, only contributes in a normal molecule only about 1%. So the idea is, so the take-home idea is up to 99% accuracy, electrons act like individual bodies. And the conclusion of this is that the energy, or the physics, if you will, of one electron is approximately equal to the physics divided by, or the energy of 1 over n of n electrons. Right? This is that idea that quantum mechanics is linear. Right? When we talk about the energies or the physics of 3 planets orbiting each other, very, very complicated. The positions of all the planets depend on each other, to the point where if you put them in the wrong place at the wrong time, they all fly apart or they all collide together. But electrons don't do that. If you put 100 electrons into a molecule and you ask what's the physics of this 100 electron containing species, the physics of it, the energy of it, looks like 101 electrons, single electron bodies. Right? This is the idea that it's linear, that it's additive. Right? That's a very, very unique property. And electronic matter in this way works really well. And that assumption is good in normal molecules up to 99%. In order to get perfection, we have to now treat electrons not like individual bodies, but things that talk to each other. But that's only going to do us one better than 1%. All right? So just by making these really simple assumptions, we've already really close to chemical reality. And all of the kind of little parts that we need to fix are very small, and they're also very complicated, right? So we have a really good, nice, simple order, it's kind of simple answer at the beginning that gets us really, really close, really easy to calculate. And what we've done is we've taken all the complicated parts and pushed them off to the side and assumed that they're really small. And in fact, they are. They're still very complicated, right? If you're going to think about electrons interacting with 100 other electrons, it's a very hard problem. In fact, it scales as 100 to the fourth, it turns out, right? So the problem becomes 100 to the fourth times harder than if you didn't assume that. So it's a very tough problem to solve. But it only gets you effectively 1% improvement. It turns out, however, just a caveat, I just want to write this very generically. I don't want to explain why that is, but it does appear. The caveat is that although particle in the box kind of gets us to like 99%, there's a ton of relevant chemistry due to that 1%. So the idea is that by and large, molecules look like just giant bodies of electrons orbiting protons, right? They have different structure because, of course, they're arranged differently. But by and large, it's just a bunch of electrons orbiting randomly around these atoms. Well, not randomly, but like waves. They have some sort of motion. But they don't really interact with each other. The electrons are all separate. Right? But the fact of the matter is that if this were the only thing that were true and electrons truly never interacted, then every molecule would look exactly the same and it would function the same. All the molecules look like particle in the boxes, and their absorption properties and their chemical reactivity and all of that all kind of look like particles in a box of different sizes with different number of electrons, right? There's not a lot of chemical diversity in that, right? It doesn't matter what atoms you have. The only thing that matters is the number of electrons you have and the length of your box, right? And we know that that's not true because mercury and iron and platinum, they act very differently than boron and carbon and nitrogen, right? And it turns out that at the energy level, and when it comes to energy, the difference between these are very small. It might be 1 to 10% difference, but all of the interesting diversity in chemistry comes from that 1%. This 1%, and so for CNO, right? For CNO molecules, organic molecules, it's about 1%. For heavy atoms, for heavy metals, it's probably closer to 10%. Okay, so the faster the electrons move and the more you have, the more interactions they have. So heavy metals, this number, the prediction becomes worse for heavy metals, but it's about 10% of the energy. But for carbon, nitrogen, oxygen, for organic chemistry, we almost don't even have to think about electrons interacting with each other. But the diversity that gives us the differences between carboxylic acids and nitriles and alkenes and aromatics, that comes from this tiny little 1%. All of that diversity comes from this. This is the diversity generating, chemical diversity generating behavior or physics. Right? If it weren't for this, everything would look right. The sociological version of this is that you when you think about a melting pot like America, if it was 100% white people, it'd probably still be America, but none of the interesting diversity of America or its culture would be apparent. But then when you start to bring in diversity into your sociological groups, you bring in a diversity of culture. It's a very small minority, but it's a very important part because it's what distinguishes your homogeneous population from being a homogeneous white mass, right? That you're bringing in a small amount of immigration into your system, and that creates this inhomogeneous kind of distribution of culture in your society. And even though it's only 1% of your population, it's a very important 1% of your population, because if you didn't have it, everything would look exactly the same. It would just look like a Midwest, the entire country would look like Wisconsin. Right? So that small minority brings in that diversity, and that's what really distinguishes it from an amorphous mass. And it's the same thing here of chemistry. By and large, electrons all act the same. They're all boring. They're all identical. And therefore, when you put some number of them, they all act homogeneously. But if we make a correction that's on the order of 1%, right, where they interact collectively, where electrons talk to each other, then the diversity comes out. It's a small correction, but it's an important one. Right? This is true across all chemistry, all chemical backgrounds. Right? This is what we call a bootstrap method, right? That if we can understand the system qualitatively at the simplest possible way, we've already gotten the majority of the way to the correct answer, and then we just need to do some work to clean up the little details and the intricacies, right? And they only constitute a small part of the energy, but they're an important part of the energy. Okay. So this is kind of the point I want to make about particle in a box. This is our amorphous blob of electrons bound in some box, like an atom or a molecule, right? By and large, molecules with electrons, they act like kind of funky shaped particles in a box. And that small difference between particle in a box and actual molecule, which can be a very, very small amount of energy, that's what generates the diversity of chemistry. Right? That very small percentage. Right? So just like, again, what the idea is in valence, while I think about the next topic we talk about, it's just like in atoms, right? The valence electrons of an atom, the electrons in the upper shell, they're what determine the chemical reactivity of the atom. There might be 100 electrons in your atom, but the only ones that determine your chemistry are the ones on the edge, right? The core electrons don't affect you at all, for the most part. And it's the same idea here. We can calculate the core physics, and it represents 99% of the molecule or the system, but that extra 1% that we've assumed is kind of averaged out or smeared out, that's actually where chemistry happens, right? Those valence electrons. Those are the things we care about. They're only a minority of the electrons in the atom, but they're the most important ones. And it's the same, it's that kind of structure, that approximative structure, is true across all of chemistry. Okay. So that's what I have to say about this part of the particle in the box. All right, the idea is that it's a perfectly good model. It gets us almost the way there, but all of the interesting parts of chemistry are left for us to figure out later. It just gives us a nice framework. So what I want to do for the rest of the class is, again, I want to mention one more postulate. I want to get one more postulate for, and that will get us into a really nice position to start our next toy model, which is the harmonic oscillator. It's a spring. We're going to think about bonds, chemical bonds as springs. We'll come up with a model for that, and it turns out to be the most important model of all physics, right? It's and chemistry. The harmonic oscillator is how we do a lot of science. It's kind of like the the physicists call it the spherical cow. I think the harmonic oscillator is the actual spherical cow of chemistry. So we'll look at that, and we'll look at it in detail starting next class. But I want to talk about one more property, one more postulate, if you will, of our wave functions and our operators to kind of close out our conversation. So the way I want to introduce this final postulate is to ask this question. All right, so let's imagine we have an electron that is pure white. All right, we'll go back to the problem set. We'll do pure white, and then we can do this for a particle in the box. We could also say localized and some energy level with energy E sub n. All right, so we can either think about a particle in a box in a given energy level, or we can think of an electron that's just white. All right, so I'm going to switch between the two today a little bit, kind of talk between both of these limits and think about our white and black electrons of our matrices and our functions and our integrals. All right, we're going to talk about them in both cases. And I want to ask this question. So the big operational question is, what is the probability that I measure this particle, this electron, and it's in some other state? All right. Now, in terms of the electrons, we can answer this, the white and the black electrons, we can answer this precisely. So if we have an initial electron go into our color box, all right, and let's just say we take the white ones, all right, and the black ones go to a brick wall. We get rid of them. All right, and now I'm going to let this white electron propagate down its line, and I want to measure it again, the color. All right? And what's the probability? Right? And I'm going to split it out, white and black. Let me actually use the colors, the proper colors for this. What's the probability that the electron after the second color measurement ends up a black one? Right? What's the probability of going from here and then here? Right? What's this probability? And of course, you guys know from problem set 1, it's very easy to calculate this. There's zero probability of this, right? Every white electron that goes through the second color box goes through the white. Right? This is 100%. And this is 0%. And this is 100%. And this is, or sorry, this is 50-50. I apologize. All right, I'm saving just a second. Okay, there we go. Sorry, we get 50% out the first box. 50% out the second box, or the first box. Sorry, a bit of lag. Right, so we know this implicitly. Right, so we know already that the probability of this is 0. %. Okay, and so therefore we can extrapolate this. So now the question is that if the electron, so let's do this question differently with particle in the box instead. So of course the idea is that we start with an electron in some state, so we'll do psi sub n, and we put it into our Hamiltonian box, our energy box. Let me make that a little cleaner. And the question we're going to ask is, what's the probability of the electron coming out in some other state, psi m, versus psi n, right, where m is not equal to m. Right? And we split them up like this. Right? And of course, we know the answer to this question. Right? It's the same thing as color. We're asking this exactly the same question as we were in the color example. Is that this is a specific pure state of energy E sub n. We're measuring its energy, therefore it satisfies the measurement theorem. So we know that 100% of the molecules are going to go across this barrier and come out the other side, and 0% of them go this way. Now you might not know mathematically why this is, but I'm doing the exact same measurement on the right-hand side as I am doing on the left-hand side. Exactly the same measurement. It's just a different variable. It's energy instead of color. So we know that this works, right? The idea is that once the conclusion is localized states which means e.g. states that are represented by one state are localized systems, localized particles, e.g. particles that are represented by a single state always exist in that state, never change. All right, once we put an electron into an energy level, as long as we don't do anything to it, as long as we don't manipulate it, will always be in that energy level. Right? Or same with color, right? Once we make a white electron, unless we change the color of it by putting it through flavor, remember flavor takes a white electron, makes a black electron. As long as we don't do that, as long as we don't manipulate it, it will always be white for the rest of time. Right? This concept has a name for it. These states are called stationary states. Right? And these are states that are unchanging in time. Right? Their characteristic does not change in time. It will always, that electron will always be white, no matter what you do. Well, until you manipulate it, right? Or this particle will always be in this energy level of the box until we manipulate it. Right? We've created what's called a stationary state. Right? It can be represented by one wave function, only one, not a sum of wave functions, not white plus black, not n1 plus n2, just a single one. It's a stationary state. All right, and my postulate is about these stationary states, the definition of them. So I'll kind of skim this page over here a little bit, and we'll start on the second page. And let's introduce our next postulate. So this next postulate, we're going to use a different term that I've never used before, but it's an important one. Called orthogonality. Orthogonality. All right, so let me make a statement about what orthogonality says. And all I'm doing is I'm formalizing the exact same conversation we just had. That once a particle is in a very particular state, it never leaves it, and it has no probability of being in any other state until you do something to it, manipulate it. But as long as we're just kind of measuring the particles, not manipulating them, it will always stay same. All right, and so there's a mathematical way to do this. So what we're going to do is we're going to assume we have two states, psi m and psi n, that satisfy the following property. For an operator, for a measurement. So we'll call that operator O, like we always have. Right? So some generic measurement O. Right? And the thing that needs to be satisfied is that when O operates on psi m, we get a real number back times psi m, right? That's an eigenvalue. All right? This just means we satisfy the quantum measurement theorem, right? The eigenvalue equation. And that O applied to psi n gives you a different number times psi n, where m is not equal to m. Right? That's the most important thing here. It's not equal to m. Okay. All right, so we have two vectors, two states that represent our system. You can think of m being white and n being black, for instance. Right? We have the white and the black, and they give +1 and -1 as their eigenvalues. So if this is true, we're also going to assume that the coefficient, the numbers, that the eigenvalues are different as well. All right, then the integral, what is satisfied always is that the integral over all space of your system of psi m complex conjugate psi n dr is equal to psi n psi m dr, right? So they're equal to each other when we swap the order that we evaluate the wave functions in the square, and this is equal to 0. So what does this say? It says that, so for functions, it says that the integral over space of two wave functions that are states of your measurement they have two answers. There's two responses when you do this integral. One is 1 if n is equal to m, and 0 otherwise. All right, why is that? Well, if n is equal to m, if these are the same, then this integral is psi squared. Integral of psi squared, and that's 1, right, by normalization. Right, this is normalization. Right, if they're the same wave function, they integrate to 1 when they square. And 0, this is what's called orthogonality. All right, why is it called orthogonality? Well, let's look at the vector case. All right, let's think about white and black. White and black electrons from problem set 1. What's the equivalent of this integral? Well, the dot product. So we'll have two vectors psi m star dotted with psi n. Right, you can think of this as 1, 0, and this one is 0, 1, for instance. Right, you have two vectors, two different vectors. And the dot product is 1 if m is equal to n and 0 otherwise. Right? This is the dot product. Right? If m is equal to n, psi m and psi n are the same vector, and you're taking psi squared, which is the length of the vector, which is 1 by definition. And it's 0 otherwise, this dot product. What does it mean for a dot product to be 0? What does dot product, what does psi m times psi n is equal to 1 or 0 mean? All right, let's assume that they're vectors. Let me draw vectors over these, just so you're clear that they're vectors. Well, let's look at white and black, for instance. So here's my coordinate space for white and black. I've drawn this a couple of times. So my white axis is my x-axis. We'll call it W, and my black axis is my y-axis. So my black-white space. And a white vector, a pure white electron, is 1, 0. Right? And a pure black electron, which I'll draw in blue, is 0, 1. Right? This is a white electron, and this is a black electron. Right? These are perpendicular vectors. Right? So what happens when you take the dot product of these? Well, this is the 0 times 1 for the first component and 1 times 0 for the second component. This is 0, 0, which is just 0. Right? So remember that a dot product measures the similarity between two vectors. Right? When you dot a vector to itself, you get the length, which is 1 in our case. And when you dot a perpendicular vector to a vector, you get 0, which means they're perpendicular. They have no similarity to each other. Right? And so this idea of orthogonality is the generic term for perpendicular. All right? This is remember these functions, the functions can be infinite dimension, right? If we represent our particle in the box wave function in terms of space, in terms of a vector, it's a vector of infinite values. So we don't want to take a vector in infinite dimensional space. That's really annoying. So we integrate instead. And the infinite dimensional equivalent, the generic equivalent of perpendicularity between two vectors, is what's called orthogonality. Right, this just means that the functions are perpendicular to each other. Right? They're like two vectors that have no similarity. Just like white and black. All right, so of course the question you might ask now is, what if my electron is a little bit of white and a little bit of black? So what if my electron, for instance, is pointing in this direction? We'll call that electron psi, with a big psi with a couple of lines like that, right? So what if what's the similarity of psi to white? Or the similarity of psi to black? Let me clean this up a little bit. I'm going to erase this thing in the middle because it's at the bottom anyway. So I'm just going to erase this just to get myself a little bit of space. Okay. So let's look at this example here with my vector psi here. Right? And I want to ask the question, what's the whiteness and what's the blackness of this electron? So let's write psi. So the way we're going to write psi is the way we've always written it. We're going to write it as CW times a white vector plus CB times a black vector. Right? And it has to be length 1. So it's normalized such that the sum of CW squared plus CB squared is equal to 1. Right? It's unit length. Remember that our white vector is just 1, 0, and our black vector is just 0, 1, right? So I'm just kind of implicitly writing these as white and black. But that's what that means. All right, it's a linear combination of white and black. All right, so the question is, what's its whiteness? All right, so I'm asking the question, what's whiteness of psi? How white is it? Well, all we have to do is take the dot product of it with respect to white. Right? So we're going to take the wave function. We have to take the complex conjugate of it, but it's real, so it doesn't really matter, but I'll just write it just to be safe. And we're going to dot it with our white vector. Right? This is going to measure the whiteness of the electron. Right? And that's going to be CW times white plus CB times black dotted with CW. Or sorry, not CW, W. Right? The vector 1, 0, I'll just write it explicitly just to be safe, is 1 times W plus 0 times black. Okay, so what's the dot product of this? Well, the dot product is going to be CW times 1 times white, or plus, that's the white component, plus the black component, which is CB times 0, which is just CW. Right, so the whiteness of psi is just CW, which is just the x coefficient of the vector. So this length right here along the axis, that's CW. And the y-axis, this projection on the black, is CB. Right? So the whiteness of a state is just dependent on how much it extends along the white axis. Right? And so the probability, so now the question, of course, is what's the probability that you take the electron and see it white? Okay? Right? To calculate that, we need psi squared. Right? So if I were to take the square of this and ask what's the probability, I'll just kind of write it here. The probability psi is observed is white. Well, that's going to be proportional to psi dot 0, 1 or 1, 0 squared. Remember, we always take psi squared. It's the length of that part of the vector, the square of it, right? And that's just CW squared. Let's see, absolute value of CW squared. Okay, so the coefficients on the vector tell you the whiteness and the blackness. And what that means is when you take the square of them, that tells you the probability of them being white or black. I know this is a lot of math, but it's very simple. Imagine now we have, let's just do an example. Psi is equal to 1 over the square root of 2 times 1, 1. Right? This is a white plus black electron. Right? And if we write that in vector notation, that's 1 over the square root of 2 times the white vector, which is 1, 0, plus 1 over the square root of 2 times the black vector. Right? And what's the probability that psi is white? Well, that's going to be equal to the dot product of psi times the white vector, 1, 0, squared. But we just saw that was the coefficient on the white vector. Right? That's 1 over the square root of 2 squared, which is 1/2. 0.5. Right? So we've just reproduced the exact answer that we expected, that a white vector, a white plus black electron has a 50-50 chance of being white or black. And by using this rule of orthogonality, we can calculate that explicitly by dotting the vector with the vector representing the state that we want, right? We want to calculate how similar is our electron to a pure white electron. So what we do is we use a similarity measurement between two vectors, which is a dot product, right? And it varies between 1 and 0. 0 means they're not similar at all, they're perpendicular orthogonal, and 1 means they're parallel, they're the same. Right? So the whiteness of our generic electron is just going to be the dot product of our electron with our pure white state. Right? And that just gives us the coefficient on the pure white state, which is 1 over the square root of 2 squared, which is 1/2. Okay, so we've been using this orthogonality idea implicitly this entire time, right? That we know that white electrons can never be black electrons and so on. But the important thing is that this is universal. Every quantum mechanical every system, physical system, satisfies this property. And what I mean by that is that when we measure the system, when we ask what's your color or what's your energy, the results that we see. So let me write that down. So the conclusion of this is, a take-home point, when we measure a system we will only receive one of the possibilities. For instance, that would be E sub n, psi sub n for the particle in the box, right? And only one. Right? So if we start with, the idea is if we start with white plus black, right, this is our initial electron, and then we measure with color, 50% of the time we get one of the two possible results, which is either 1, 0 or 0, 1. And then every time we measure color after that, we always get 1, 0. It never changes. Right? I could just keep on going, right? And the same thing for black.
Cypher?
Yes, ma'am.
So, if it's 1, 1, does that mean it's both black and white?
So that's a good question. So the answer is, so that's a very good question, and it depends on how you look at it. So you're right. I call this white plus black. The fact of the matter is that if you treat the electron like a vector, it has equal component white and equal component black. But when we don't know anything about the color of this electron. So when we measure the color of the electron or the energy or any property, it only can come out as one or the other, right? Because classically, when we measure our particle ourselves with our eyes, we don't see a white plus black electron. We see a white or a black one, either or. And so the idea is that the initial state of our electron is both. And then when we make our measurement on our color box, the system, what we say, collapses into one of the two possibilities. And we only see that one. And then that electron forevermore will always be that white or black electron. So the idea here is that before measurement, so measurement again happens here at the green light. This is our measure. Our system is represented by both because it can be either one, because when we measure it, we get 50% one and 50% the other. And so once we measure, we've localized our electron probabilistically in either black or white, and it will always be that way. So you could say that the electron initially was black and white, and that when we measured the color, we've collapsed it into one of the other two colors. But that's not really that fair, because by labeling an electron white or black, we're making an assignment ourselves with our mind and our eye. Right? So black and white in some ways are only defined with respect to their individual vectors. These 0, 1, and 1, 0, these are the things that we see. And they're the only things that we can see. We never see a 1, 1 electron. What a 1, 1 electron means is that there's a 50% chance that it's going to come out white or 50% chance it comes out black. So it's not really fair to say that it's a black plus white electron, because if we were to assign black plus white, that means we're using our eyes and saying, hey, it's half black, half white. But you can't do that, because when you do that, the electron's going to either come out as a white or a black, not both. So this is what's called wave function collapse. The idea is that before you measure a particle, it's in what we call a simultaneous superposition. It's in all possible states. And then when we measure it, it localizes to one of the states, only one of the states, and the probability at which it does that has something to do with its coefficient, right? This dot product that we're taking. So what that means is that this idea of white plus black, so as Janine is asking, right, this idea of is white plus black, it's not really fair to call this a white plus black electron. Rather, what these numbers are referencing is a representation of the measurement probability that you get out. It's a representation of the result that you get. A 1, 1 electron says that if I measure it, it's going to be 50% white or 50% black. That's the chance. That's all I know about it. That's all I can measure about it with color. It's the only thing I can measure. So by saying that it's white plus black, this really means that it's an electron in a state, in a probabilistic state, weighted equally between white and black. So it doesn't have, its color is not simultaneously white and black, because color can only be white or black. Well, what 1, 1 says, what this electron says, is that statistically this electron is prepared in such a way that when you measure it, it comes out white 50% of the time and black 50% of the time. That does not mean it's white plus black, because that description of it being white or black only happens at the point of measurement. The only time we can say white or black is when our color box spits out a 1 or a -1, black or white or black. That's what color means. It's the measurement tells you if it's white or black. So calling 1, 1 a white plus black electron is somewhat unfair, because it doesn't spit out a 1 and a +1 when it goes through the color. That's what a white plus black electron would do. It'd give you the result for a white and the result for a black. That's not what it does. When you put one electron in there that's in the 1, 1 state, you either get 1, 0 50% of the time or 0, 1 50% of the time. There's only two colors, black and white. There's no sum of the two. But the way that the probability in your measurement system works, right? These vectors, so these vectors in some ways, they don't represent the particle itself, the state of the particle, but rather the potential, the probability. It's a measurement of it's a representation of the results that you'll get from the measuring that electron, right? So what you really should think about when you think about electrons or atoms is that they're not necessarily, the only time that they're localized in, say, a color or an energy is when we make the measurement. Before that measurement, before we ever touch it, right, it's by itself, never been touched, never been looked at, never been measured, the electron's not white plus black. It's not in a particular energy level. It's undefined. It's in all possible states. It can be in any possible state. It's simultaneously white and black. It could be at 0 energy. It could be at infinite energy. It could be right here in this room. It could be on Mars. Whatever position, whatever thing you want to think about. Any observable or measurable you can think about. Before you measure it, it can be anywhere. And what does the wave function tell us? Well, the wave function tells us what it predicts in some ways. It quantifies what the results of our experiment are going to be about measuring it. And so electron that's in a state of 1, 1, which I kind of naively call white and black, but it's not. All this is really saying is that when I put this electron and I actually measure it on my box, when I actually assign the word color to it, which is what happens at measurement time, that it's going to be 50% of the time white and 50% of the time black. And the only possible way that can happen is if the electron initially is in all possible states, period. That's what problem set 1 suggests. So you have to think about the wave function not as a physical representation of the molecule, but rather it's a piece, an object that represents the outcome of your measurement of that particle. All right, it tells you, it gives you a prescription and an answer for what you'll get in your measurement. It's not really, and so what we're doing by saying it's 1, 1 is that our measurement for it is 50% white or 50% black. Right? So naively I call that white plus black, but it's not really white plus black. Because that 1, 1's not representing the particle. I mean, it represents the particle, but it's representing the particle from the point of view of our color experiment. It's completely defined by the experiment that we have. The experiment we have has two possible results, white or black. So there's only two numbers. And we can have any combination of numbers as long as they're length 1. But the fact of the matter is that before we ever measure it, the electron's in all of those possible configurations. It's just depending on how we set the electron up and experiment up, we get a different answer, and the wave function that we measure, or the square of that, represents that result measurement. Right, so when I write the wave function as 1, 0, this means that it's an electron that 100% of the time when I measure it will be white. That's all that means. It's still the same, this 1, 0 electron is the same electron as the 1, 1 electron. There's nothing different. Electrons are identical. But what's different is I've prepared them in such a way that I've changed the statistics and the probability of my measurement. In the 1, 1 case, the electron is arranged in such a way that I get a 50-50 chance. But the 1, 0 electron is exactly the same electron as the 1, 1 electron. In terms of its physical identity, they're indistinguishable. But it's in a system, it's in a state where every time I measure the color, it's 100% white. All right, so the wave function represents our measurement results. It encodes our measurement results. But every one of these every electron is exactly the same. There's nothing different between the two. They're all indistinguishable. So there's really no difference between a white plus black electron or a white electron or a black electron. They're all the same. It's just about the probability of whether measuring in one state or another. And so therefore, it's not really fair to call them white plus black electrons. In the same way, it's not really fair to call them white electrons or black electrons. They're just electrons. And electrons are in all possible states all the time until you do a measurement. And I know that's a really hard thing to get around in your head, conceptually. And But that's the fact of the matter, and that's the reality of it, and that's one of the, and some people have a real problem with this, because what it means is that if I look at this bottom example here, where I've taken a 1-1 electron and I've split it, and it's magically become 50% of the time a white and 50% of the time black, that sounds like I'm destroying a white plus black electron to make, on half the time, a white electron, half the time a black electron. I'm doing some sort of destructive process by measuring this, right? I've collapsed my system from a superposition to a set of pure states, right? Like, you've destroyed the system in some ways. Right? By measuring it, you've destroyed it, because you've converted the system from 1-1 to either 1-0 or 0-1. Right? So that, obviously, there's a change there. I think everyone can identify that. And so there's a conceptual problem with that, right? That the measurement destroys the initial state and gives you a set of different states that the initial state is composed of, right? And the initial state only tells you the probability that it'll end up in one of the final states, 1-0 or 0-1, white or black. That's all it tells you. People have a real problem with that, because it's like you're destroying a particle and then recreating it in a different framework. And so this is called the collapse of wave function collapse. And this is one of the weaknesses of the Copenhagen interpretation. This method of using psi squared and all of this stuff, this interpretation we're using, these postulates. It's the biggest weakness of it, and people have problems with that, because it feels like you're destroying something, that you've taken a white plus black electron, as Janina calls it, and destroyed it into either a white electron or a black electron. You've lost information when you measure it. And so people have issues with this, and it doesn't seem very physical, but it's one of the things that we just have to deal with. So you just have to get used to that. There's nothing you can do about it. So there are other ways to get around that problem, but you kind of sweep the problem out under the rug, and then you introduce complications and other postulates. So we kind of have to make a compromise where we want to kind of make things, where things start to look really weird and not physical. And this is the case. And in case of the Copenhagen interpretation, in case of the way we're doing physics and chemistry in this class, this is where the problem arises in our interpretation. That it feels like when we measure an electron, we're destroying it and creating a new electron of a very specific category. And that our representation of the electron, this 1-1 vector, isn't really a meaningful representation of the physical object. It's a representation of our experimental results. Right? 1-1, all 1-1 says is 50-50 chance. So the wave function is actually a representation of the physical results of the of our experiment. And we're just representing it in the context of our experiment. So people have problems with that, because you're not actually measuring. So what are we doing here? We're not actually writing down things that represent the molecule. We're writing down notation that represent the results of our experiments. Right? We're just encoding our experimental results into these numbers and saying, hey, this is what our particle is. The 1-1 particle is an electron that's, when you measure, is 50% white and 50% black half the time. That's not a particle. That's an experimental result. So anyway, there's this philosophical issue, and this is where I'm going to end for today. This is a philosophical issue about this, is that the wave function squared, again, isn't representative of anything other than your measurement probability. It's a representation of your experimental results. It's not a representation of the actual particle. So when we watch a wave function evolve in time or in space or something, we're watching how our experimental results are changing in time as we measure it. We're not actually tracking the particle, we're tracking how the probability of observing the particle changes. And you can imagine how certain realistic people who, think particles are real and all of these things are physical objects that you can hold in your hand, we just can't. They have a real problem with this, because we're not actually doing physics of particles, we're doing physics of experiments, experimental results. That our numbers and our wave functions encode the results of our experiments. They don't tell us anything about the molecule or the atom. All right? I don't want you to get caught up on this, because it's gonna be a problem. You just have to understand that we have to make compromises here. Is that real life, physical reality is beyond our little peanut-sized brain understanding. That we live in a world that is dominated by classical mechanics, this idea of Newton's third law and all of this junk, right? These are the things that we've grown up and learned, and this is entirely contrary to it. And the fact of the matter is that this is not wrong. This provides the exact results we want, and it's incredibly precise, more precise than anything we've ever done in history up until this point. It's very, very correct. So the only conclusion that I personally have is that the way that we think about things is wrong, and that thinking about particles as physical objects with definite properties only works to a certain extent. And here we're starting to observe where that breaks down. Okay, so we have to kind of like take the red pill and kind of free our minds from this concept that a 1-1 vector is a white plus black electron. That's how our classical minds think, that this is a half white and half black. But that's not the case at all. All this is saying is that the electron is in a state where when we measure the color, it's going to end up being white 50% of the time and black 50% of the time. That's all this says. Okay, so I'm gonna kind of mix and mingle these things, right? Because we're still talking about a particle, so it's still a representation of physics, real representation of measurements. But what we're going to have to get used to is that in chemistry, microscopic chemistry, when we study chemistry, we're not actually touching and manipulating molecules. We're doing experiments, we're measuring properties of molecules, maybe we're manipulating molecules, and that the wave functions are going to tell us the results of that manipulation or that process. All right, we can get all of the information we need about what's going to happen in our experiment from this wave function. It might not be a physical representation of the actual physical object in front of you, or well-defined one at least, but it will give you all of the information you need to figure out what happens when you do your experiment. All right, so that's the way we're going to move forward. So we're going to kind of do things in kind of an abstract way. We're going to think about molecules as things that we can measure, things that we can manipulate, and all we can do is read out the results of those manipulations and those measurements. And we're going to build an image of what the particle or the molecule or the atom looks like by looking at those results, right? We're going to back calculate what the atom or the molecule structure looks like. And it's going to look funky, it sure is, and it's not going to look like what we expect, but it agrees with all of our experiments to incredible precision, so there's no reason to think it's not true. All right, so that's a different way to think about science, I think, than you've probably ever heard before. But it's an important one. And you can get away in this class by conflating the two ideas together. The idea of a particle and a measurement. Right? You can get away with that. And I'm going to be lazy about it in this class. But the fact of the matter is that in some ways the wave function only is a representation of the measurements of a particle, not the particle itself. Okay, this is an experimental theory. All right. So anyway, I got off track. We're 5 minutes over. So I'm done for the day. I will go ahead and upload this for everybody. Starting on Wednesday, we'll probably start thinking about the harmonic oscillator next. Start thinking about chemical bonds. And that'll put us in a good position once we're done to start thinking about the hydrogen atom. All right. You guys have a nice snow day. And I'll see you guys on Thursday.
All right, have a good day, Professor.
You too. You too. Thank you.